Hello, Professor. Professor Leandro, you are at Technology Innovation Institute. The event is happening right now. Tell us why you are here and what are the insights you're sharing at this exciting event.
Thank you very much. I'm the acting chief researcher of the Quantum Research Center. We're hosting and organizing the Quantum Technology Symposium. This is the first event of such level in the country, and I dare to say in the region, in terms of bringing top-notch specialists from quantum computing, quantum sensing, quantum communications from all around the world. This is a scientific event mostly, but it also has industry panels and business discussion, and in fact, also policy discussions. And we're organizers and hosters of this, but at the same time, we're also presenting work. So we're giving talks about our main R&D activities. There are also poster sessions and discussions. We're having presentations on quantum algorithms, on quantum computing hardware, on quantum middleware, which is the software, as well as quantum sensing, quantum communications, and quantum physics.
Quite a lot of information that is. Professor, let me ask you this
Yeah.
question. Tell us in simple layman words, what is quantum computing all about? Why should we be excited about this technology?
Great, thanks for the question. Um, the computation means to process information, and we're used to conventional computers like we have in our laptops or in our mobile phone. Essentially, there, what you have is the bit, that's the unit of information, it's a 0 or a 1, and that's what you use to make all these calculations and processing that we have in the digital era that we're in now. Now, quantum computers is a machine. This will be machines that they will exploit the quantum effects that happen in nature at the microscopic level. When you look at nature at the microscopic level, at the level of atoms, at the level of electrons, at the level of photons, which are the particles of light, things behave in a different way. And there are these quantum effects. There is something called the quantum superposition principle, which is this effect whereby, for instance, an electron can be in two places at the same time. There's the famous Schrodinger's cat experiment where a cat can be dead and alive at the same time. Now imagine you can do the same thing with an electron or with an atom. And in fact, what quantum computing tries to do is to use this superposition effect, this quantum superposition effect, to process information. So now imagine instead of a bit that can be in either 0 or 1, you have a quantum bit, the so-called qubit, that can be not in 0 or in 1, but it can be both in 0 and 1 at the same time in a superposition. So this opens a whole new space of possibilities in terms of processing information. And in particular, we have identified the community of quantum computing theory and experiment in the last couple of decades. We have identified computational problems that are very important for industry and commercial applications that are very, very hard to solve for conventional computers, but for which quantum computers will be able to solve these problems in an efficient way, in a much, much faster way. We're talking about problems from drug design to optimization of energy distribution to implications on financial applications, and of course, optimizations for carbon footprint reduction. There are many, many applications that will benefit from this new technology.
Professor, what level have we reached with this technology right now? What are some challenges that we face in scaling this quantum algorithms for real world applications?
Yeah, so quantum algorithms, like I said, so you try to design routines or subroutines for solving problems that exploit these quantum machines, right? And these machines are still in their infancy. You really need to scale them up. So we have different types of experimental platforms, and most of them are in sizes of tens of qubits to a few hundreds of qubits. That's still very little. And also the quality of those qubits. These machines are very susceptible to noise. They're very sensitive, so they are affected by noise and thermal fluctuations in such a way that you have a system that you want it to behave in a quantum way to display these quantum effects that we were mentioning. But if it's subject to noise, it loses its quantum character and becomes an ordinary classical processor of information, and then you lose what you want, right? So it's a big technological and engineering challenge to scale up these machines while at the same time preserving these so-called fragile quantum effects, right? So quantum algorithms is interesting because you really need to think of ways of processing information in a different way, taking into account these quantum effects, and these algorithms will require large quantum computers to be run. However, there are things that we're learning from the theory of quantum computing that also gives new ideas for classical algorithms that can be deployed today. So there's an entire subfield of quantum algorithms called quantum-inspired algorithms. These are subroutines, these are protocols that can be deployed on nowadays CPUs and GPUs, but it's a new generation of classical algorithms that take components from mathematical things that have been discovered in the study of quantum computing theory. So this is a very strong activity in research activity in the quantum algorithms division at the Quantum Research Center in TII here in Abu Dhabi. And it's interesting because quantum-inspired algorithms, they are not just an intermediate step towards the final goal of fully quantum algorithms, but also they have the potential of delivering some commercial value today for certain niches. And the research activity consists in identifying these niches, right? So we're talking, for instance, of applications in computational fluid dynamics or even in protein design. There are certain optimizations that enter into the design of proteins for which quantum-inspired algorithms were having very promising results in that direction, right? So there's these two sides of the story. On the one hand, we do applied research and development of quantum-inspired algorithms today, and on the other hand, we're studying quantum algorithms that will have an impact in 5 to 10 years when we will have large-scale quantum computers becoming online and becoming available.
Professor, let me ask you on what is your research in this area? How are you contributing to TII, and any specific activity that is very interesting to convey to my audience on quantum computing?
Right. Like I said, I am theoretical physics from background, but nowadays my research is at the interface between computer science and quantum physics. So I'm a specialist in quantum algorithms and also with a background in quantum information and computation theory. So I come from the origins of the theory of quantum computing. I've been doing research on this since my master's, already 2 decades ago. And what we do is, again, there's our activity involves lots of components from mathematics, lots of components from computer science, and of course from quantum physics. Our work is theoretical. We do lots of numerical simulations. We try to simulate the performance of these quantum computers and estimate the resources, for instance. That's something very important because if you have a big industry, you want to know when quantum computers will actually be useful. And so we expect that we will be able to solve some problems much faster than conventional machines, but all we have is numerical simulations of the performance of a quantum computer because we still don't have a large-scale quantum computer available, right? So lots of our work is concerned with estimating the amount of resources, like how big a quantum computer will have to be in order for us to deliver some commercial value to ADNOX operation or INEX operation or some energy company in the country or some financial institution or also in the healthcare system, right? So lots of what we do is design of algorithms, estimation of resources, quantum resources for these algorithms to work, and also a big activity that we do is how to characterize quantum devices, experimental devices. Nowadays, experimental devices, they still suffer noise, and you need to understand this noise so as to be able to calibrate them better and also to do error mitigation for coming from those noises, right? So all of these activities require a huge theory support, and this is done in the Quantum Research Center by the Quantum Algorithms Division that I've been heading the last 4 years, as well as in collaboration with the Quantum Physics Division. We have 6 different divisions. Some of them are theory, some of them are experiment. What I've been contributing to Abu Dhabi and to the country, there's no other team in the country doing this research. It's really with expertise on quantum algorithms. There's a team of almost 25 specialists in quantum algorithms in the Quantum Research Center.
Professor, how soon would we see this technology being popularized? When I'm saying popularized, I mean, see, when I speak of AI, everybody is interested simply because there's a ChatGPT out there and it has consumerized the entire space of AI. How far are we from there?
Right. When will we have the ChatGPT moment of quantum, right? That's the
Yes.
trillion-dollar question, right? There are different estimations, and also it depends on the type of application that you. Very likely, what will happen is that it will be gradual. As the technology scales up and we increase the number of qubits and the quality of qubits, some applications will become available before others. And the first ones to become available will not be the ones that will make most of money. So, for instance, people are expecting applications on computational problems that have implications on more like science, like I don't know, certain systems, certain models from physics that we don't have computational power to really understand them. So quantum computers will provide that power, but it's not that which will give the trillion-dollar market cap that we're expecting, right? After that, what we expect is commercial applications in chemistry and in material science. So in chemistry, you want to simulate molecules, or in material sciences, you want to simulate a crystalline structure. And so you can imagine applications where we use quantum computers for doing simulations of other quantum systems, namely a molecule or a crystal. And after that, we will have more and more advanced and abstract applications, like, for instance, problems for machine learning. Quantum computing will also contribute to more efficient machine learning models that will impact further in AI, or, for instance, predicting stochastical process in the financial system. So we will see all these applications in a gradual way, right? So some people expect the first applications in a horizon of around 5 years, 5 to 10 years, and the advanced applications in an horizon of 10 to 15 years. Now, the truth is that this is a race. You have different quantum platforms across the globe. This is a global effort. You have the academic sector, governmental sector, and industry all pouring money, research, and talent into this. And history shows that things can happen in a very unexpected way, right? But I think that we may start seeing some commercial applications from 5 to 10 years, and some advanced commercial applications in 10 to 15 years. This is without taking into account quantum-inspired algorithms that I was mentioning that can start delivering commercial applications earlier, right? So it's really an interesting moment of history, because quantum computing is nowadays interesting to investors. It's tremendous, the amount of money that it's being poured into this field by VCs and big companies and startups, governments. But at the same time, it continues to be a field that requires lots of research. So you have this conjunction of investors, as well as governmental players, as well as talented people coming with purely scientific interest, right? So that's the current state of the art of the quantum computing field.